The Arrhenius equation is K equals A e to the power of minus EA over T. This shows an exponential relationship. Now, let us look at this graph for activation energy. The peak here represents the activated complex. This is the activation energy. We are looking at the intermediate step in a reaction. The graph shows the energy profile for activation energy. This energy is needed to form the activated complex. This graph is the Maxwell-Boltzmann distribution. The peak shows the most probable kinetic energy. This graph shows how increasing temperature accelerates reactions. The blue curve is at temperature T and the brown is at T plus 10. This graph shows how temperature affects reaction rates. The blue curve is at temperature T and the brown curve is at T plus 10 degrees. Let us look at the graph in detail. The slope of the line is minus EA over R and the intercept is ln. Hello, we are calculating activation energy and we substitute our values. This gives us EA. Then we find A. A catalyst is a substance which increases the rate of a reaction without itself undergoing any permanent chemical change. Hello, let's look at this graph slowly. The solid line is without a catalyst. The dashed line shows a catalyst lowers the energy needed. Let us look at integrated rate equations. We integrate the differential rate equation. This gives us concentration versus time. A zero-order reaction is one where the rate of the reaction is independent of concentration. Rate R equals minus Kt plus R naught. Let us look at this graph for zero-order reactions. The line is straight with a slope of negative K. This shows constant rate. Section 3.3.2, the rate is proportional is integrated R K plus ln R naught. Hello everyone, let's look at alternative forms of the first order rate law. First, for the rate constant K, we use this form. Next, the base 10 logarithm form. In first order reactions, the graph of natural log of reactant concentration versus time is a straight line. The slope is negative K. This is a worked example for calculating the rate constant of a first order reaction. Hello everyone, today we will discuss half-life period. Half-life period is the time taken for a reactant's concentration to reduce to half its initial value. In zero order reaction, half-life is independent of initial concentration. In zero-order reaction, half-life is independent of initial concentration. But in first-order reaction, half-life depends on initial concentration. Let us look at example 1. The rate constant is 5.5 times 10 to the power minus 14 per second. Let us discuss pseudo-first-order reactions. When one reactant is in large excess, it stays constant. For example, the hydrolysis of ethyl acetate. Hello everyone. Today, we will look at this summary table for rate laws. Notice the difference in the differential rate laws for order 0 and 1. Hello. Today, we will explore the temperature dependence of reaction rates. This graph shows how the rate increases with temperature. Collision theory of chemical reactions, developed by Max Strauss and William Lewis, explains reactions through molecular collisions. Collision theory explains that for a reaction to occur, molecules must collide. This is based on the where molecules are like silicon. Let us look at the initial rate expression from collision theory. The rate is the collision frequency, ZAB, times the exponential factor. The effect of orientation is very important in chemical reactions. Proper orientation allows molecules to react and form products. This diagram shows a chemical reaction. If the molecules have improper orientation, no products form. But with proper orientation, the reaction proceeds successfully. Let us look at the summary. The Arrhenius equation describes the temperature dependence leaping of reaction rates.